morning session. So today we have the first lecture by Joaquin Turiaci from the University of Santa Barbara, and he's going to talk about quantum aspects of 2D dilaton gravity. So the talk is going to be like the lecture is like something like 50 minutes, and then we can have like a few more questions like in the end. So there are 3 lectures, so there are two more. Mm-hmm. So Joaquin, please.
Okay. Yes. Thank you very much for the invitation, and yeah. So the first part, for 1 lecture and a half, probably I will talk about 2D gravity, and then I will, in the second part, I will talk about applications to higher dimensions. So this will be roughly the plan. So first I will talk about Joaquin tidal bond gravity, and I will talk about quantum aspects and non-perturbative effects that I will explain now. Then I will talk about the formations of Joaquin tidal bond gravities and do a similar story for more general 2-dimensional theories of gravity. And then in the second part, in the second part, I will talk about these 2 points of how this is a good approximation to certain problems in higher dimensions. Okay, so first I thought I would start with a quick list of why, at least for me, JT gravity is interesting. So first, at least recently, it became popular because it's a sector of the dual theory to some quantum mechanics model like SYK. And it was a good toy model to study things related to chaos, scattering near the horizon of a black hole, traversable wormholes, etc., that are very hard to study in higher dimensions. Another application is that captures some physics of near extremal black holes in higher dimensions. That would be the second part. And more relevant to the first part, maybe, is it's also a toy model to study the role of space-time wormholes. And a central theme will be to try to understand what is the meaning of the gravitational path integral and how it leads to disorder of the holographic dual in a way. And I'm not going to talk about this, but also a very important recent application was to compute the page curve for the case of evaporating black holes. But I'm not going to talk about that, but it's certainly related to the topic of understanding wormholes better. But okay. Okay, so I will start with Joaquin tidal bond gravity. So as I said, we will focus on 2-dimensional theories of gravity. So first question is, what are they and how can we parameterize them efficiently? The most general two derivative action is this, where we have this dilaton phi, the metric, well, the curvature r. And these are the most general terms that we can write down with 2 derivatives with arbitrary functions f1, f2, and f3. But this is unnecessarily too general because we can do a Weilbrecht scaling of the metric for some function omega of phi that can be used to set f2 to 0. And under some assumptions, we can also redefine the dilaton to call whatever it's multiplying r. And then the most general theory of 2 derivative dilaton gravity is given by this action with phi r term and a dilaton potential u of phi. So when I talk about 2D dilaton gravities, I mean theories with actions of this type. Okay. So in the case of Joaquin tidal bond, it corresponds to a very specific choice of dilaton potential, but just a linear dilaton potential. And the action is given by these 3 terms. The first one is just a topological term that it will be useful, but yeah, so you can think of it as a term with a constant dilaton, that is this phi naught. The second term is the proper JT term, that is phi r plus 2 phi, so this is a linear dilaton piece. And the third term is the Gibbons-Hawking-York boundary term, that is it's important, very important in ADS2. Just to mention quickly why this is relevant to higher dimensions. So when you look at near extremal black holes in higher dimensions, deep inside the throat, the geometry is very generally ADS2 cross, well, S2 in 4D, or well, you can have other transverse spaces, but in the simplest case of, let's say, a near extremal riser Nordstrom. And in this case, the dilaton comes from the area of the transverse space. And the phi naught should be thought of as an extremal area, and phi as some small fluctuation around the extremal area. Okay. So the important feature, so first of all, I will analyze quickly some classical aspects of JT gravity just as a brief introduction for those of you that maybe haven't been, maybe haven't been working on this. An important feature is that the JT mode breaks the symmetries of ADS. Of course, maybe I should have emphasized it. I've been talking about holography, so I will be interested in asymptotically ADS2 spaces. In a way, the profile of the dilaton defines the physics of the problem in the way that I will explain. And if we look at the classical equations, they have this form for a general dilaton potential. And this equation comes from varying the dilaton, and this one from varying the metric. And for JT, this simplifies drastically because the second equation, which comes from varying the dilaton, implies that the metric has a constant negative curvature given by this. And the solution for the simplest topology, at least, is just a hyperbolic disk that I will parameterize by R and theta. And just for concreteness, I will take this to be the metric. So if you want to think of this as a Euclidean black hole, then basically the horizon is at the center, and the boundary of ADS is this black circle at the boundary of the hyperbolic disk. So you should see this as a Euclidean black hole.
Joaquin, sorry. So I guess these equations were like, only for the JT case, right? So U is now just linear in this case, right?
Yeah, so this is for any dilaton potential, but it's special about JT that this term becomes just a constant.
Right.
And it doesn't couple to the dilaton in a way. Yeah. And if you add, one thing I could mention also, if you add matter and the matter couples to the metric but not to the dilaton, then it also doesn't affect this equation that comes from the dilaton. So this JT is really very, very simple in this sense. Yeah. Any other question? Okay. So before solving the equations, we need to decide the boundary conditions that we want to put at the black circle at the edge of the hyperbolic disk. And we will pick Dirichlet for both the metric and the dilaton. So the dilaton at the boundary will have some very large value that I will parameterize as gamma over epsilon. And the length of the boundary will have also a very large value that I will parameterize as beta over epsilon. And the point is that you should think of epsilon as some holographic cutoff that you're sending to 0. And gamma is renormalized dilaton, and beta is the renormalized length. So when we think about holography, beta will be the inverse temperature of the dual quantum mechanics living in the boundary. So the solution for the dilaton can be put in this form using the symmetries of ADS2. So this is what people usually mean by when they talk about JT as breaking the symmetries of ADS2, because this profile of the dilaton that we're taking depends on R, and this is the thing that breaks the symmetry of ADS2. And that's why people refer to it as nearly ADS2, as opposed to higher dimensions where you can keep the symmetries, the conformal symmetry exactly. Here in 2 dimensions, it's important that we break them. And we will cut a patch of the hyperbolic disk in a way that satisfies this boundary condition. So the simplest case that I draw here is a circle with some cutoff, some RC. So this RC is the location of the circle, where R is the radial coordinate. And if you remember, the metric had a sinh of R. Sorry, I can show it. This sinh of R. So if I look at it close to the boundary, this is exponential of 2R. So the condition of the length being fixed is determining this. And then when I pick this same cutoff for R in the solution of the equation of motion of the dilaton, it tells me what this constant phi h needs to be in terms of the boundary condition gamma and beta. And this phi h is the dilaton evaluated at the horizon, which is the center, and is related to the temperature in this way. And sometimes I will keep gamma, sometimes I will set it to 1, because you can see here that gamma has dimensions of length, beta has dimensions of length, so we can always choose units in which gamma is, let's say, 1, and then it's absorbed in a rescaling of beta. Okay, so to understand why the role of the dilaton is so important to understanding the metric, so we can look at the Lorentzian space. And the profile of the dilaton basically determines whether there is a horizon, what is the temperature, etc. Even though, as I said, the metric is always ADS2. So, for example, in Lorentzian, we can draw the space as global ADS2 with 2 boundaries, which would be the region here. But if you look at the profile of the metric consistent with the equation of motion, you'll see that the boundary curve, what you want to call the boundary curve, is this red line. And this covers the Poincaré patch of global ADS2. So we would call this a 0 temperature solution. On the other hand, if we have another profile of the dilaton, that it's actually it's the analytic continuation of the disk that I just draw, then you get a picture like the second one, where you have these 2 boundaries, this red line and this red line, where the dilaton goes to infinity. And then if you look at regions, for example, here, the dilaton goes to minus infinity, so that cannot be a boundary. And when the boundary curve is picking this smaller patch that is called the Rindler patch, then you can see that the geometry has 2 horizons, and you will call this a black hole, or with the horizon here. So I just wanted to emphasize that it's keeping track of the profile of the dilaton is important for a physical interpretation of these solutions. And let me draw it here. So maybe I should have made a picture, but so what I mean here is that when we look at the disk, you should think of the disk that I drew before as a Euclidean preparation of this thermophile double state, basically. And so that's why when I talk about the Euclidean disk, I will think of it as a black hole. Okay.
I have a question.
Yes.
Yes. Is it possible to deform JD gravity such that, in fact, you can get a complete conformal case?
No, so the problem, if you try to do that, is that there is not a well-defined. There are no CFT ones. So, for example, okay, there are a lot of ways to see this, but one simple argument to see that this is a problem is that if you have a theory that is exactly a CFT without breaking the symmetries, then you can look. Can you see here what I'm writing?
Yes.
Yeah. Okay. So you can ask what are the consistent density of states that you could have, and the only 2 forms that you can have is this or this, where here you have some number and here you have another number. This is the only thing allowed by conformal symmetry. But if you look at this one, this diverges. If you want to count the number of states at 0 energy, it diverges, so it's bad. So you would say, okay, I don't want this term. But then you end up with a theory of only ground states. So it's more like a topological theory in a way.
Nice.
So that's why you want to break the symmetries of ADS2.
So it means that assuming ADS-CFT, then there should be no scaling variant solution, even though I add various kinds of matter fields, or I can deform the dilaton potential. It would be impossible to.
Yeah. So this is very different. As maybe a picture that I like is from the near extremal black hole in 4D. So let's say you have a near extremal black brane in ND and you have a D3 brane. Then you can take the decoupling limit where, what does it mean? Just look at the throat that is ADS5 plus S5, and you can take a limit where where the terms that break the conformal invariance of the throat disappear, and then you have like the pure ADS5 and you have a pure CFT that is well defined. But there is something special about ADS2 that when you want to take that decoupling limit, you either get a trivial theory or you are forced to include fluctuations around the. You need to include the leading term beyond the decoupling limit, and that leading term is like JT gravity.
I see.
That's some mental picture.
I see. Thank you very much.
But sorry, Joaquin, can I comment on that just a second? So I don't fully agree with this, right? Because so it depends very much like on the potential of the dilaton. So there are cases where the potential admits an infrared fixed point. So you can still have infrared fixed points in 2D dilaton gravity.
Yeah, sorry. Yeah, maybe I agree. But maybe what I want to say is that then you'll get a theory that is too simple for the kind of physics that you want to describe, right?
Sure, but I mean, for example, extremal black holes can be described by this kind of infrared fixed point. Yes, so there are scale invariant solutions. Like if there is a suitable potential, there are scale invariant solutions in 2D dilaton gravity.
Yeah, but maybe I would say, so I agree with that, but maybe I would say that you are only describing the extremal states, and
that's right.
You're not allowed to
right.
look at fluctuation. Yeah.
I'm sorry, I'm confused. So if I am allowed to deform this dilaton potential and also allowed to couple some proper matter field, then can I get scale invariant solution in 2D?
Yeah, so that okay. You don't even need, for example, if you remove the JT term, then you could say that the scale invariant solution is to have a profile of the dilaton that is constant, right?
Right.
Sure.
But then, yeah, what I want to say is that then the problem is that if you try to look at fluctuations or something like that, then it becomes ill-defined for. And yeah, so it depends on what you want to describe, I guess. I mean, you have the people that work on, I don't know, like this.
Yeah. Your example of deleting this potential clarified my question. Thanks.
Okay, this will come back in a lot of different ways later, so we can keep talking about this during the 3 hours. Okay, is there any other question? Okay. So okay, now I will talk about JT gravity beyond the classical solution. So obviously there are no propagating degrees of freedoms in 2D. And the nice thing about JT gravity is that one can see very explicitly that the theory reduces to a boundary mode. Basically, the idea is that before I picked a circle as the boundary, but I could pick any shape that satisfies the boundary conditions. And I need to include that, and that's like a boundary graviton in a way. You can think of it that way. And the way to see it is that in the case of JT gravity, the dilaton acts as a Lagrange multiplier. So to see this, you can first integrate out the dilaton, and that kind of localizes to metric of constant negative curvature. And in the case of the disk, there is just one, which is this one. When we look at higher topologies, it will be more subtle. And then we can cut the patch of the disk in different ways. And the point is that the Gibbons-Hawking term will give different weights for different shapes of the boundary. And the circle that I draw before will be the one with minimal action, but in general, you have to sum over all of them if you want to do the exact calculation. So I will go over this very quickly, but we can parameterize the boundary curve in this way as a function of r of tau and theta of tau. Tau is the proper distance in the boundary that I will want to identify with the SYK time, let's say, Euclidean time. For convenience, I introduce this f of tau that is just a rescaling of theta. And we integrated out the dilaton, but we still need to impose the boundary conditions on the metric. And that's just, you pick the metric, you evaluate it on the boundary, you ask that it's a constant, and what that gives you is a relation between r of tau and f of tau. So this is a simple geometry problem that you can do. Oh, what did I do? Sorry. Where is it? Okay, sorry about that. Yes, so now you have that the only degree of freedom is this f of tau that we will call the Schwarzschild mode. And to understand this, you can, so to get what is the action of this mode, as I said, you integrate out the dilaton first. So the only bulk term is this phi times r plus 2. So after you impose that the surface is constant curvature, that bulk term is 0. And everything you have is the boundary term, which I wrote here. And so you have this term. So if you remember, let me see. So I don't have to. So this comes from the length of the length element of the boundary curve. This is the dilaton. If you remember, there was the integral of phi k, and this is the extrinsic curvature -1. And this one you should think of as a holographic normalization to make it finite as epsilon goes to 0. And if you insert f of tau and you compute the extrinsic curvature, then you get a finite answer, and it's this Schwarzschild action that I wrote here. Where this, okay, I didn't write it down, but this is the well-known Schwarzschild derivative you probably all know. So that's what this bracket means. And this gamma is the renormalized dilaton, and this acts as a coupling of the Schwarzschild mode. So after this procedure, you end up concluding that the path integral on the disk is given by the path integral of this boundary mode f with this action. So this integration manifold over f is over diffs1, meaning that these are the diffeomorphisms of the circle, modded by SL2R because you have these symmetries of ADS2 that basically there are a lot of different curves that are related by SL2R, and you don't want to overcount. And the boundary condition is that being a diffeomorphism that when tau goes to tau plus beta, f goes to f plus beta. So it's okay. And the correct measure for the JT path integral is this one. That okay. The details it's not going to matter, but so this is a natural measure over this space that was introduced by Alexeyev and Chatashvili. And it was the reason why this is important is that it was understood by Stanford and Witten that this allows to do this path integral by localization. And finally, in a paper of Sachin and Stanford, they explained that this measure is what you actually get from the, if you are careful about what is the measure of JT gravity, then you want to reduce it to the measure of this Schwarzschild mode, and then this is the correct answer. So as I said, the path integral is one loop exact with this measure. So first I wanted to quickly mention the saddle point. So the saddle point is this. If you look at what are the equations of motion and you solve them, you'll find that it's this. And this is the circular boundary that I drew before. And the classical action is just to evaluate. So this is the topological term. So this will be proportional to the parameter phi naught. Yes, and so here I have gamma, that is the prefactor. I have the Schwarzschild evaluated on this solution, it's just a constant given by this, and then I multiply by beta of the length of the circle, and I get this answer. So the thermodynamic that follow from this partition function is this. So the entropy will have some very large extremal constant S naught, and the corrections are linear in the temperature. And the specific heat this is gamma, which is the renormalized dilaton. And the energy has this like extremal energy, and the deviations go quadratic in the temperature. And in terms of degrees of freedom, the density of states is given by this. It's e to the S naught and e to the square root e. This is the semi-classical answer.
May I have a question?
Yes.
So all of this is in Euclidean situation, but can you actually, can I simply make a analytic continuation to Lorentzian case?
Yeah, you can. I mean, there are some subtleties, especially in a paper of Harlow and Schafferis that, like in Lorentzian, you would imagine that you have two independent Schwarzians, but they have them coupling between them. Okay, well, I just want to say that there is the issue of factorization that is hard to see, but okay, ignoring those issues, in general, you can take the Euclidean answers and analytically continue to Lorentzian, and you'll get the sensible answers.
I see. So at the level of path integral, but not for this subtle points. Also for these subtle points, can you actually continue to Lorentzian case? And
yeah, and then you'll get this picture. Okay, maybe I'll draw it here. But so this picture that I drew before, that it looks like this, and then you have something like this. And then if you look in Lorentzian how this boundary particle evolves, it will do something like this. And that's why you would call this in Lorentzian a black hole, where here is the horizon. So you can track down the trajectory of this boundary particle in Lorentzian signature satisfies the same equation. Yeah.
So here, your saddle is f equal to tau. This is a classical solution.
Yeah.
And when I make a continuation, then tau is it.
Yeah.
So it becomes a complex.
Yeah.
So it has a complex saddle. That's it.
In terms of, yeah. It's a little confusing to think of the of the Schwarzian in Euclid. I mean, you can look at the classical solutions the most useful way to think about it is to look at the classical solution in terms of what is the trajectory of the boundary particles. That's the
first I analytically continue to Lorentzian, then I solve the equation of motion.
Yeah, and you look how it happens from the point of the Schwarzian path integral is better defined in Euclidean. So if you try to analytically continue and then solve it exactly, there might be a little. Well, I guess that's the usual issue of the Lorentzian versus the Euclidean.
Yes. Okay. Thank you very much.
Can I ask a similar question here? For the topological term, for instance, or for a disk, we know how to evaluate this Euler number, basically, by regularization. And for Lorentzian case, is there a way to deal with this kind of topological number there?
Yeah, so okay, I'm not going to do it in real time because it's very confusing, but you just need to be careful with the factors of I. Yeah, maybe in this case it's not that, well, at least also if you try to do it in DS2, it's very confusing, but if you're careful about the factors of I, then you get the right answer. Just to multiply by a real S0. But
okay.
Yeah, you just need to be careful about where the factors of I are.
Excuse me.
Yeah.
Yes. So in this case, there's no phase transition. I mean, there's only this black hole phase.
Yeah.
And actually, so no something like Hawking phase transition occur in this case.
No, not in this model.
Okay.
So
even if we deform, sorry. I mean, even if we deform this theory a little bit, but still, you will not get any.
No, that would be interesting. So the deformations, it would be interesting to see if one can hook up some model with Hawking phase transition, but I don't know how to do it.
Okay, thanks.
I will talk about that later. Okay, so maybe I will go a little bit faster, but this is so the partition function is this term. This is the 3-level term, And if you compute the one loop, you get this, where you get this factor of beta to the 3/2 that you can think of as coming from the zero modes, counting the zero modes of the metric. That is, you have 3 because you have SL2 in ADS2. But in any case, this is the answer. And from here, you can extract the exact density of states. That is this sinh of square root E with this E to the S naught prefactor. So it looks something like this. You have this semi-classical behavior at large energies. And as you go to lower energies, quantum effects become important, and you have this square root edge. That will be important later. Yes. Okay, so maybe I will try to be brief, but I wanted to make some comments about what happens when you add matter. So as I said, I want to put matter that couples to the metric, but not to the dilaton. That's the simplest situation. And that's the one relevant for higher dimension when you think of it as a near extremal black hole. And so in this case, you can integrate out the matter and you'll get a correction to the effective action that depends on this is the boundary conditions for the matter field. So this is like the source of the boundary operator. And what you get is this. So this is like the 2-point function. And the point is that you need to, it couples to the Schwarzschild mode. So you need to integrate that out as well. So even though the matter is free and it still couples to gravity through the Schwarzschild mode. And what you call the Schwarzschild theory 2-point function, or the ADS2 2-point function for at least free fields, is the expectation value of this observable in the Schwarzschild theory. So this is a very natural formula, and you can look at what form it has in the saddle point, and then we get the SL2R invariant 2-point function, which is this. But when you do the calculation exactly, you go away from this answer because the conformal symmetry is broken. So this is just a semi-classical. And the exact answer can be obtained, is given by this formula that we computed in a paper with Thomas Mertens and Hermann Berlinde. And some partial results were obtained before by this Adlan, Baggers, and Kaminer. So we're here basically, oh, I didn't write it, sorry. Let me write it here. So I'm using that the energy is k squared over 2 gamma. So k is a parameter of the energy that is just convenient. And this is just the density of states. Mu of k is the density of states written in terms of k instead of the energy. E to the minus tau E of k1 is like some Euclidean propagation term. This is the second one. And this is like the matrix element of the boundary operator after you couple it to gravity. So in Lorentzian signature, if you analytically continue, this answer decays exponentially in time, semi-classically. This is like a quasi-normal mode decay. And there's some nice features that when you look at quantum effects, this exponential decay becomes a power law. So if you were thinking of the information paradox in the language of Maldasena's eternal black hole paper, this tells you that this is inconsistent with the unitary quantum mechanical dual. And when you include quantum effects, it's a little better, but not quite. You still have a problem. So that's a little motivation for what I will do next. That will be to add higher topologies. So okay, this is a comment, just a quick comment about the 4-point function. So there are different channels from the free field kind of Witten diagrams in ADS2, and they're all given by their own Schwarzschild path integral. These two are very simple and kind of factorized in an energy basis. And this one is a little bit more interesting and is given by a non-trivial, you can think of it as a scattering matrix here that is given by I'm not going to write it down, but it has a very particular formula that is a 6J symbol of SL2R. But the only point I want to make is that there is an exact answer, and when you take the semi-classical limit, it's responsible for the Lyapunov growth of this diagram. Okay. So
can I ask a question? People normally say this 2D JT theory is not UV complete, and so Well, it means basically something goes wrong if we go to the UV, I mean UV limit. Can you clarify?
Yeah, so I think what goes wrong, I don't know if you would say, yeah, you can say UV, but the thing that goes wrong is if you want to interpret it holographically. Like in principle, there is nothing wrong with this, but if you want to interpret it holographically, it's bad because, well, you can, where is it? I guess even here, like, I mean, this is a quantum mechanical system. So if you want to get an answer consistent with something computed like a trace over a Hilbert space, it should be a sum of delta function, right? You should have a discrete spectrum. But instead you get something continuous. And there is no space in the quantum mechanics. Like in general, you are okay with the continuous spectrum because this would be multiplied by a large volume, and you're talking about things per unit volume or things like that. But you cannot interpret it that way here. So the only way this makes sense is if you imagine that S naught is infinite, basically. And what the higher topologies term will do is to have access to effects that are finite in S naught. So yeah, so I think the JT gravity on the disk is problematic for that reason.
But Joaquin, can I ask something on that? So if you change, like, I mean, the dilaton model again, right? I mean, so if you take, for example, the one that you get from 3D gravity, right? I mean, to 2 dimensions. Yeah. So would you say that it's still inconsistent? Like, I mean, so in that case, I would say that it's UV complete. Of course, the UV completion is not a quantum mechanics model. It's like it's some kind of higher dimensional theory. But
yes, yeah. So yes, yeah. So you need a UV complete theory that is not literally the 2D, necessarily the full 2D theory. Yeah.
Right, but for the Joaquin Teitelbaum, I mean, that is even that is not true, right? I mean, so JT gravity, I thought, I mean, it's not UV complete even in that sense.
No, I think it. Well, maybe if you want to think of it that way, you have to add gauge fields from some KK modes.
Right.
But there is a sense in which you will get a UV complete dual of pure JT gravity, and this is going to be a matrix integral that I'm going to explain. So it has its own problems. You have things like disorder and ensemble average over theories, but okay, that was the next point.
Well, can you explain a little bit more how to get UV completion out of this JT?
I will explain that now. Yeah.
Oh, okay.
Yeah. So the idea is to add a sum over topologies. Yeah. Okay, so first a quick comment. So, okay, I was motivating the problem by the decay of the 2-point function with matter, but I'm going to focus on pure JT gravity. So then I cannot talk about matter, but there is something similar that is the spectral form factor, that is this quantity. So it's basically like a 2-point function where you remove the matrix element that would be multiplying here, right? And in JT gravity, it decays in time forever as 1 over time cubed, something like that. But in a good, well-behaved theory, you expect it to saturate at some point. So this is kind of similar to Maldasena's version of the information paradox. And to reproduce this behavior where it saturates, we will sum over topologies. And this is the insight of Schenker and Stamp. Okay.
Sorry, may I have a question?
Yes.
So, you mentioned on OTOC so it's about OTOC of matter fields.
Yeah, but now I will forget about matter.
So
just mention it to say some more things about the Schwarzschild theory, but now I'm going to look at pure JT gravity.
I see. So when you talked about this OTOC, then is it possible to forget the matter fields and consider only the Schwarzian degrees of freedom to compute the OTOC? Or
yes, that would be, yeah. I mean, you can think, okay, I will write it here. You can think that from the point of view of the Schwarzschild, you have an observable, which is this f dot tau1, f dot tau2 over sinh squared of f1 minus f2. And then you want to do the path integral over the Schwarzschild mode of this observable. And and this is unobservable inside the Schwarzschild theory, right? And one motivation is that it comes from integrating out matter, but you might just want to study it by itself. And the OTOC appears from putting two of these guys and doing an analytic continuation in doing the correct analytic continuation to go to Lorentzian signature.
I see. So is there any reference on so that I can learn more about this?
So yeah, you can look at the paper of Maldacena, Stanford, and Young from 2016, because there what they did was to compute this OTOC semi-classically using these methods and check that it has Lyapunov growth and all that. Then in a paper with Mertens and Berlinde, we computed the exact path integral. But maybe that's not, I mean, if you want to see the conceptually what's going on, maybe that's unnecessary to have the full answers. So probably if you look at the Maldacena, Stanford, Young, that would be good enough.
I see. Yeah. Thank you very much.
Yeah, sure. Okay. Okay, so as I said, we will consider the more general case of summing over topologies, and this spectral form factor involves the product of two partition functions. So let's generalize it to any number of boundaries, so any number of partition functions, and I will write it like this, where the reason why I'm putting brackets will become clear soon. So this is the path integral on these spaces with this, where each of these boundaries it has the holographic boundary conditions of dilaton blowing up and the length blowing up. So I can use the topological term to sum over genus. That is very simple. It's just the number of handles, and they're all weighted by this factor. Where this is the genus, this is the number of boundaries. And so e to the minus s naught is kind of like a string coupling in a way for this theory. And we will want to compute these prefactors, Z, Gn. So the contribution for some fixed topology and some fixed number of boundaries. And the idea is to integrate out the dilaton first, and then you have a sum over hyperbolic surfaces in the same way as before. But the new subtlety is that now you have a moduli space of hyperbolic surfaces as opposed to having just one, and you need to take that into account. But it's very simple because the bulk action is still zero. So all you need to do is to basically count hyperbolic surfaces. And so a useful way to think of it is to cut and glue the geometries. And the idea is that all the holographic boundaries have a geodesic that is homologous to the boundary. So you take a surface, in this case with three handles and three boundaries, and you cut it in this way. And then you do the path integral here, 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 and here separately, and glue. These terms we will call the trumpet, following Schenker and Stanford. And it's some partition function that will depend on beta and b. And this will just be counting the, so in this geodesic boundary, there is no Schwarzschild mode because k is fixed to 0. And the path integral here is basically the volume of the Weil-Peterson modular space of Riemann surfaces with this number of geodesic boundaries, number of handles, and it will depend on the length of the boundaries. So, okay, this is what I just said. So the path integral in the trumpet you can do using the same procedure as before. You integrate out the dilaton, you have some Schwarzschild mode that is not the same, it's a different Schwarzschild, or it has a different action, which depends on B. But it is still one loop exact, and it gives you this answer. And okay, and the rest is the Weil-Peterson volumes. Okay, so okay, maybe I will skip this, but this is just a definition. The Weil-Peterson volume is it's just a choice of volume in the space modular space of surfaces. And then you get the partition, the full path or this contribution to the path integral by gluing. So you integrate over the length of the geodesics. You multiply each trumpet, in this case it would be 3, and you multiply by the Weil-Peterson volume. And after doing these integrals, you get the prefactor ZGN. And from the details of what the Weil-Peterson measure is, you get that this is the correct measure to glue. And the point that Schenker and Stanford justify that this is the right measure that you get from the JT path integral. Okay, so let me finish in the last couple of minutes. I can give a couple of examples of how the calculation works. So the simplest is the double trumpet, and this is the one that contributes to the spectral form factor that I mentioned before. So here, this is even simpler. We have a single trumpet. Sorry, we have two trumpets, but we are just gluing two trumpets without any extra surface. So this is what we get. So this is B, and we integrate over B, and we have these two trumpets, and this is the answer. This gives a contribution to the spectral form factor that grows with time. Basically, because what you have to do is to put B1 to be like beta over 2 plus IT, and you put beta 2 to be beta over 2. So going back minus IT. So going back to what I said before, I will assume that I can do all these things and they're well defined. But then this term will give something that at late times grows with T. So this is what they call the ramp. And if you compute a two-point function in this geometry, it will also have a term that grows with time. So this is the leading non-trivial topology that is giving you some aspect of the unitarity that is lost in the disk. And okay, it has the form of the double scale matrix integral that I will mention later. So this is the first issue. So this is a Euclidean wormhole, and this is non-zero, and it spoils the factorization of the boundary dual. But we will talk about that next time. Second simple example is the disk with one handle. So here I'm just taking the disk and adding one handle. So this appears as a non-perturbative correction to the disk. This is the disk. So here I rewrote the Schwarzschild path integral, and the contribution from here comes exponentially suppressed in S0. And it's computed again by integrating. Here I have B, and this term gives you the Peterson volume with one boundary and one handle, and this term gives you the trumpet. And okay, this Weil-Peterson volume is known, and you can do this integral and you get this answer. This is not very illuminating, but I just wanted to put it as an example of how to do the calculation. Something you can see here is that as opposed to this term, here there is no exponential term. And that happens because there is no classical solution on this geometry. The same with the double trumpet. So we are doing an exact integral over off-shell configurations of the metric. Okay, so how much time do I have? Do I have like 2 minutes, something like that?
Yeah, sure. So and then we can have like 10 minutes of discussion or something like that. But yeah, I mean, you can take up to maybe 5 minutes if you need.
Okay, yeah. So I finished this part of the.
Sure.
Okay, so yeah, of course I don't have time to review this, and it's probably not super relevant for what I will say later. But I just wanted to say that these Weil-Peterson volumes are known, not explicitly, but the recursion relation was derived by Mirzakhani, and it looks like this, and it's pretty ugly. And the idea is that you just cut and glue the hyperbolic surfaces, but the reason why this is so complicated is that you need to be careful about the mapping class group of the surfaces. That's very non-trivial to do, but you can see here that this relates Weil-Peterson volume with some genus and some number of boundaries to volumes that have either lower genus or lower number of boundaries. So this recursion is, what I want to say is that it's solvable. Like if you know the first three terms, which are these, then if you put it here, you can consistently compute all the terms. So with this recursion, you can compute all the partition function of JT gravity for any number of boundaries and handles. Now, there is a nice observation that of Einar and Orantin, that it is that this recursion simplifies when you write it in terms of the Laplace transform of the volumes. So here I integrate over B, and now I have functions of Z, where I have one Z for each length. Okay, it's just a formula. But when you write WGN, which is this Laplace transform, then the recursion becomes much simpler. It still has the same structure of giving you a certain genus and Gn in terms of simpler quantities with either smaller genus or smaller number of boundaries. But this formula is much, if you try to actually, I don't know, do it by hand or put it in mathematics and try to solve it, this is much simpler. And the seed of this recursion now is that the case of the disk, let's say, with no handles and one boundary, has to have this expression. And the case with no handle and two boundaries has this expression. And this is at the heart of the results of Sachin and Stanford, I'm going to say probably next time. And the idea is that this recursion is precisely the loop equation of a matrix integral. And this W is the resolvent. And this W0, is the disk density of states. And when you write it in terms of the eigenvalue, which is basically Z equals to I square root E, then this becomes the JT gravity density of states. Okay, so the next thing I was going to say, maybe let me say the conclusion of the matrix integral quickly, and then so next time I can go faster in just 2 minutes, I guess. So what Sachin and Stanford did last year was to figure out a way to do the path integral and the sum over topologies. And then they realized that the path integral of JT gravity, which is the left-hand side done in the way I described, is equal to a matrix integral that I wrote in the right-hand side, where I integrate over a matrix H with some measure mu of H. And for each holographic boundary, I insert the trace of e to the minus beta H. So this is a very unusual type of holography where this matrix has to be interpreted as a Hamiltonian. Each boundary is inserting the trace of the e to the minus beta H of the boundary, like a thermal partition function over this Hamiltonian. But the new aspect is that now you have to average over the Hamiltonian. And in a way, I would say that this is the UV completion of pure JT gravity, which is a matrix integral. So in this way, the continuum density of states and that those issues are related to the fact that you have a sum over delta functions, but when you average over H, it became a continuous after averaging. But and this parameter e to the S naught should be thought of as an average level spacing of each realization of the Hamiltonian. Let me see. Okay, probably I will stop here and I will explain it a little bit more tomorrow. Okay. Thank you.
Okay, thank you very much, Joaquin. So maybe like people have some questions now, we can discuss like for a few minutes before we take break for the next talk.
May I have one more question? So you had a figure of this double trumpet.
Yeah.
And is that a classical solution or not?
Huh?
Is it a classical solution or not?
No, it's not. Yeah, that's
it's not.
That's interesting. So yeah, so there was a lot of confusion, I think, in the past, or whether these geometries contribute or not. So these are these are the simplest geometry that contributes to the non-factorization. Oh, can you see my? Oh, I guess my screen is freezed. Sorry, give me a second. I wanted to. Sorry, one second. Okay, can you see it now?
Yes.
Okay. Yeah. So if you want to compute the 2-point function of like the product of two partition functions, beta 1 and beta 2, then yeah. So you have a solution that is the two disks, And this is fine because this is factorized. I mean, this is just a product of two numbers, supposedly, if you have a single dual.
So that's a classical solution.
Yeah, those are classical solutions, but then you have this Euclidean wormhole that is not a classical solution, and it contributes to the connected product of two-point functions. So, so these are not classical solutions for the same reason why, basically, if you look at global ADS, this is like a identification of global ADS too. And there is no classical solution where the dilaton goes to plus infinity and plus infinity at both boundaries. If you try to look at classical solutions, you will get that you plus infinity in one and minus in the other. So, for example, in the paper of Maldacena and Chi, they try to do this kind of wormholes, but they need to add interactions between the two boundaries.
So I'm a bit confused. So in what sense this is a saddle?
This is not. This is not.
It's not a saddle.
This is a saddle. This is fine. This is, but this is not a saddle.
It's not a saddle. I see. So after you do all the path integral, it appears to.
Yeah. So this is a sum over of shell configurations that contribute to the connected piece of this.
I see. So all the other contributions, if I add more boundaries and if I have more handles, all of them are off shell and not saddle.
Yes.
I see.
Yeah, that's why I wanted to show that when you compute them, there is no exponential term that you could interpret as an action, right? So that's one way to see. But so there is a metric, right, which is the hyperbolic cylinder. But what I wanted to say is that there is no classical solution for the dilaton consistent with the boundary conditions. If you look at the dilaton, it will have this profile.
So what does it mean? It means that for the metric, it's on. You would say that it's on shell, but the other one is not.
I mean, the metric is on shell, but because you're integrating out the dilaton, so it's kind of, there are no metric fluctuations. It's only
so it's
trivial, but the dilaton, there is no solution for the dilaton.
I see. Thank you.
Yeah.
So Joaquin, maybe you're going to talk about this later on. I'm not sure, but large part of this discussion seems to apply specifically to the JT gravity, right? I mean, so for example, what happens if you deform the dilaton potential that you wrote in the beginning, this function u of I?
Yeah, that's for next time.
Okay.
Yeah. So maybe just to mention it quickly. So we wrote the paper with Henry Maxfield and some independent work by Witten, where you can deform the. Maybe I will say it quickly and then it will go faster. So the problem is that if you cannot integrate out the dilaton first, it's hard to do it because you need to integrate over the metric and the dilaton. And there might be a way to do it, but I don't know. But the way that we found is so you have the dilaton potential to be this, and we will add terms that are like this, say alpha phi. And then when you have the path integral, and you can do a Taylor expansion in this coupling, and then you will have the path integral over the metric and the dilaton, and you will have insertions of this e to the alpha phi, some number of them at each order in lambda. Let's say lambda k, and here you have k terms, and here you have you will have roughly the JT answer. And the idea is that this one now you can do with the JT terms, because if you integrate out phi, you will get that you localize to metrics that have r+2 equal to some delta function at some location, some x, whatever. And so then you can study the formations of the potential by looking at JT gravity with defects. That's the idea.
Right. So what has been done in this case then is it's basically perturbative in lambda, right? And so
so
perturbations.
It's perturbative, but the nice thing is that you can resum it exactly.
Okay, I see.
Yeah. So then you can we can basically compute this whole thing. Well, not for any genus, but at least for the disk. And then you can do the sum over k exactly. Yeah.
Thank you.
Yeah.
Any more questions? Well, if not, maybe we just take a break, like half an hour break, and then we come back at 10:30. So Joaquin, thanks again.
Yeah, thank you.